Thank you very much. IPAM, thank you for this event. I know it was a challenge to make it work online, but everything runs so smoothly. So thank you very much to the organizers, also to the people that invited me. It's an honor being here and see such great talks by great mathematicians working on this challenging problem. So again, so this talk will provide an overview of some of our work that we have done during the last year. During the last years, I will say 5 to 7 years. And we will go from zero-sum to non-zero-sum games, Stackelberg games, graphical games, and see how reinforcement learning can help solve these complicated equations. Okay, so this is the outline. So of course, I will introduce why this problem is important. First, I will derive my Hamilton-Jacobi equations, which we all know, for different kinds of games. So zero-sum, non-zero-sum, Stackelberg, and graphical games. Then I will provide some iterative model-based solutions. Then I will incorporate reinforcement learning and what we have done over the last years to develop some unique methods that it works like adaptive control, but also has optimal components. Then what I will do is so all these things will be about nonlinear systems. And then I will develop a partially model-free solution to Hamilton-Jacobi equations that they don't require the drift dynamics. For example, if you have a system with this x dot equals fx plus gxu plus kxt, blah, blah, blah. So your fx will be unknown. And we will not identify it, but our method will be model-free in a way. And of course, when model-free for complete systems, if you don't require also the knowledge of gx, kx, or any nonlinear function that you have in your dynamics. So of course, one very famous algorithm is the algorithm by Watkins. But this was developed mostly for Markov decision processes in discrete time space. So everything that I will talk about, they evolve in continuous time systems. They're continuous time systems, and all the actions are continuous, and the state is continuous. And finally, I will show how what happens when you have erroneous actuator data in your Q-learning framework. And then, of course, I will conclude the talk about future work. So, of course, I'm also available for interruptions. So anytime you guys want to stop me, I'll be happy to hear any questions. And then this can actually potentially lead to a discussion. Okay, so before I start my talk, I want to give a brief overview of some things. So learning, they live in their own bubble. Okay, so back in the days, the people in control were using neural nets for approximation or for a feedback loop. Nowadays, they start working on reinforcement learning, actor-critic structures, blah, blah, blah. And of course, if you combine that with optimization, then these two things, they come together with what is called approximate dynamic programming. And approximate dynamic programming, in a way, it solves the process of dimensionality by using approximators. And I think I saw this also in G-Talk, where he used some approximators, feed-forward neural nets to approximate some functions and then solve the cross-dimensionality in a way. And so again, these two bubbles, they come together with what we call approximate dynamic programming. And then there's another bubble that is very important, especially for us that we do controls, that is called distributed control, okay? And of course, solving games that they're in a graphical sense. For example, I communicate with some neighbors, okay? I get some action from my neighbors, and then I have my own cost, which is distributed. So then, this is an area of research that we're all working, and then you will see at the end of my talk, I will talk about what we call graphical games. Okay, so online learning, why we want to use online learning? So we will need to know to learn from mistakes. Of course, we will have a performance, or reward or punishment, and then we will improve that over time, okay? And I know learning nowadays is becoming really hot, especially from the perception side, where deep learning has shown a lot of success. For us, we will use reinforcement learning, which is the merge of optimal and adaptive control in a way. And I want to get data from my environment in an intelligent way, okay? I want to operate under circumstances that I haven't been programmed before. So for example, let's say you have an offline optimal control problem. So what we have to do is you have to solve the Hamilton-Jacobi-Bellman equations offline, and then you have to put it on the system. But what happens when your system changes mass? What happens when your gas gets reduced? What happens when you don't know exactly the dynamics, all these things? So, or what happens when you have a potential adversary who actually changes your learning mechanism in terms of your actuator and sensor data? Okay, so this is what I said also. And this is actually a very vague connection of RL with what we call reinforcement with controls. So of course, whenever I talk about a controller, I will mean that I have an actor who actually takes a decision. Okay, and then if I talk about reward, I will see that I will call mostly about critics. So I will use actor-critic frameworks, and I will get data from the environment. Okay, so throughout the years, we have worked in many things. So, but what I'm interested more is what you see in this figure by David Silver, where reinforcement learning actually was in the middle of optimal control machine learning, reward system, operant conditioning, rationality, and operations research. So you see that reinforcement learning will probably be something that we will all use, as also we saw from Wayne and Stock, we will all use to solve these complicated Hamilton-Jacobi equations, okay? And again, as I told you, what we do from the control side, we use actor-critic structures, okay? So the actor implements the control policy, and the critic evaluates how good my control policy is. So I remember when I was in Santa Barbara, so I saw, I was talking to somebody and I told him, okay, so we use actor-critic structure. So we have 2 actors, 3 critics, blah, blah, blah. So they told me, oh, this looks like a movie. Okay, so after this funny comment, I was like, yeah, probably. Okay, so another thing that I want to point out is since we work on learning-based controllers, so I want to differentiate also this, what is automatic, what is adaptive, and what is autonomous. So automatic, of course, is, you can think about the classical controllers, but they're not that smart, right? So you can think about the PID controller. Adaptive is when you adapt to different uncertainties. And then autonomous is when you add cognition. And cognition will come probably from a learning mechanisms that for our scenario will be a reinforcement learning mechanism. So I know nowadays in this rainbow of structures, people they claim, okay, I'm autonomous, but I have to do a PAD, or I'm autonomous, but what I do, I adapt to uncertainties. So I think as long as you add a cognitive mechanism, so then you're completely autonomous, because as humans, that's what we do, right? We have cognition, and based on that, we make decisions. Okay, so now let's start going to the math. So first, I will describe zero-sum NAS games. Okay, so again, I will describe these things based on the controls perspective. Okay, so of course, in the controls perspective, we will have some nonlinear dynamics. Okay, and in such scenario, we will have 2 competing players. Okay, so one will be our controller, and the other player will be a disturbance. And of course, for those of you who are familiar with robust control or H-infinity games, so you can think that these zero-sum games, they're very close to H-infinity control. Okay, which you can think that this is an infinity game in infinity sense. Okay, so of course, we have a unique equilibrium solution, but we can have multiple equilibrium strategies. Okay, so from now on, whenever I talk about my dynamics, I will say that for the zero-sum games, I have x dot equals fx plus gxu plus kxd, where fx, g, x, and kx are nonlinear functions. Okay, and for this one, we want to design u such that we want to control our system subject to worst case disturbances that are given by D. Okay, so again, since this is an H-infinity control, the first thing that will come to your mind, okay, so it's a minimax game. Okay, so I want to minimize as a U player. I want to minimize to find my U such that I do the mini over the max disturbance. Okay, of course, you can think that our cost will be convex in U and concave in D. Okay, that's an easy way to think about it. Okay, so, and for controls, let's say I want to achieve regulation. Okay, so I mean, controls we like mostly to stabilize systems. So let's say that I want to go to the origin. Okay? So as I said, now we will define the value function. And so Qx is a nonlinear function of x. U transpose RU is how I penalize my control. And then minus gamma squared D squared is the worst case disturbance. That's why we have the minus there, because we want to make it as concave. Okay, so as controls people, we want to find first the Hamiltonian functions. Okay, so the Hamiltonian functions is what you see as the inside the reward function, is the reward function plus, you can think this one is the Lagrange multiplier, and then my only constraint will be the equality constraint that comes from my dynamic. Okay, so actually the first value function that you saw, it's a mini-max minimizes with respect to U and maximizes with respect to D. And that this Hamiltonian actually merges the equality constraint. It makes the problem with this unconstrained. Okay, so of course the optimal policies of this Hamiltonian can be found by using stationarity conditions. I'm sure we all know these things, okay? And then if we put this back into the Hamiltonian, then we will have what is called Hamilton-Jacobi Isaacs, which is given by this guy over here, okay? Of course, as you all know, this is almost impossible to solve, doesn't have a closed form solution, and especially in a high dimension. Even for simple systems, this is very difficult to solve. So people, they have tried to solve it in an offline structure, and you will see pretty soon what I mean by that. So before I go into the solution of these problems, what I will do is I will define you everything, I will formulate everything in an offline structure, and then I will tell you about the different kinds of solutions. Okay, so now let's say that I have a non-zero-sum NAS game, okay? So here I have an arbitrary number of players, and in this way I can model any cooperative or non-cooperative objectives. And every player will have their own objective. Okay, so so here's my dynamics. Okay, so here your U, you don't know if actually it's a minimizing or a maximizing player. Okay, and again, f of x and g, j, x are again nonlinear functions. So now every player U has its own cost function. Okay, so here I miss my I in my j. Okay, so every player will minimize its own cost function. Okay, and then eventually I will converge to a NAS. Again, this now gives rise to even more complicated equations, because now all these equations, because you have n of, if you have n players, as you see in my picture, then all these equations will be coupled. Okay, so then you will have what is called coupled Hamilton-Jacobi equations, which again they're even more difficult to solve. And another thing that I want you to think about when I formulate this problem is what happens when you have interactions of agents in a graph. Okay, so here what you see here is a centralized. Okay, but what happens when you have interactions in a graph? Okay, and of course, since we also want to work in distributed control problems with an optimal performance, this is actually very useful for us. And so, for example, you can think that we want to reach eventually consensus. Okay, so that I think your delta that you see here is for the people working in consensus. It seems familiar. So Aij is the adjacency metrics. Xi, Xj is the way I communicate with my neighbors, and J is in the neighborhood I, and the Gi is the pinning gain if I talk to the leader or not. Okay, and again, since we're controls people, I want to take the derivative of that and then find my dynamics. And again, this thing now, it's we prove that we developed a graphical NAS, which we call it interactive NAS, and then this has to do with how many steps I have to uncontrollability. And these are what we call distributed coupled Hamilton-Jacobi equations. Okay, so now, of course, you can also, as you remember what I told you, is we can have different kinds of players. Some of them, they're good players, some of them are bad players. So you can write in a graphical game, you can write as the team players, okay, in the neighborhood, plus the opposing team players. Okay? And then this is just a funny graph, okay? So now let's talk about how we will be able to solve such equations. So people throughout the years, they have used policy iteration, okay? So policy iteration is you start with an admissible policy, okay? What I mean by admissible policy is a policy that provides a stabilizing controller. So let's say that I run my system and I know that pole placement will work, okay, it's stabilizing, and then I want to find my optimal controller in a nonlinear sense. And of course, also stabilizing, it will also provide a bounded cost, okay? So, but again, these are expensive equations, okay? So, because every time I have to solve a Lyapunov equation, okay? So I have the policy improvement and the policy evaluation. So the policy evaluation, I have to solve a nonlinear Lyapunov equation, okay, at every step, which is not the best thing to do. And of course, in order for me to simplify things, I will get motivated about from this policy iteration, and I will use approximation structures. Okay. Okay. Of course, one problem with this one is that we require complete knowledge of the system dynamics. Okay. So what you saw there, f of x, gx, kx, all these nonlinear equations, they need to be known. Okay. And of course, we also require, as I said, since we do policy iteration, we require knowledge of initial stabilizing policies for every player, because every time I start my policy iteration, I have to find the U that stabilizes every player in the system. Okay, so let's have in a pseudocode. Okay, so again, we start with initial stabilizing policy, U0, but you can pick the way you want to design it. Let's say I want to do pole placement or PID. And then I will iterate, okay? And let's say I start with a U, I assume that D0, okay, which is my bad player into the system, and then I solve the Lyapunov equation that you see in the yellow, okay? And then I will do that, and then I update my D, okay? So you can think this is the zero-sum game that I described before, okay? So my U is my minimizer, and my D is the maximizer, okay? So again, I start with a U, then in the inner, this is the outer loop. In the inner loop, okay, I set my D equals to 0, and I solve for my cost, and then I update my D. Now, before I end this loop, I also update my controller, okay? And then I run that forever. But again, as you see, the tricky part here is that I have to solve this equation here, which is not the easiest thing to do, okay? It's simpler than actually solving it for solving Hamilton-Jacobi-Bellman, because here you have fixed U's and fixed D's, but it's not the easy thing. Okay, so now, of course, I can do the same for my non-zero-sum games. Okay, again, I have to start with initial stabilizing policies, okay, for every player. Again, let's say I have n players, and let's say all of them are minimized. Okay, so every player has its own cost, and then eventually, if you pick all the J's together, you will eventually converge to a NAS equilibrium. Okay, so here, now it becomes even more complicated because I don't have to solve only one equation, which is the Hamilton-Jacobi-Isaacs that you saw before, but I have to solve a bunch of them, which is n coupled ones. And then I have to do that, okay, for every time instant, okay? And then again, I update my all my n policies, okay? So again, I start with my n policies, I solve my n tuple of value functions, v1 to vn, and then I update my policies. Okay? Again, easier than finding a solution to the initial couple Hamilton-Jacobi-Bellman equations. But again, this requires lots of computation. Okay, and then similar thing for my graphical. Now it's like more distributed. Okay, let's see what we actually contribute to this literature. So we have observed that when you go back to the equations here, for example, and then you substitute your V's with with approximators, in a similar framework that Chi developed. So then you will see that instead of having these nonlinear equations and their PDEs, you make them algebraic equations with respect to the weights. Okay, let's see what this happens. Okay, so, and one famous theorem that we can use is Wistow's high order approximation theorem. Okay, so what I will do, I will write my V, okay, as an infinite number of weights, and this is multiplied with the basis function. And of course, since I cannot really put an infinite number of weights, I will have an approximation. Okay. So eventually, I want to substitute these things in my Hamilton-Jacobi-Bellman equations or the coupled Hamilton-Jacobi equations, and then find a way to tune these WIs such that we guarantee stability and convergence. Okay. So again, since we don't have the optimal ones, right? So we will assume that we have current weights. Okay. So from now on, we will call this approximator here as the critic. Okay. And then you will see that if I substitute these things back into my Hamiltonian, okay, so you will see that they become linear with respect, algebraic equations with respect to the weights, okay? And of course, since I don't have exact knowledge of my V and I cannot put infinite number of bases, this will give me some error, okay? Okay, so of course, as I take this error, as I take more bases, okay, again, here I will use a single layer neural net, okay? So a single layer neural net where, a single hidden layer, okay? So I have an out, I have an input, hidden layer, and I have an out. And when I take my basis to infinity, then of course I can say that I converge to my optimal solutions. Okay, so remember that in my Hamilton-Jacobi-Bellman equation, if I substitute my optimal U and my optimal D, or Hamilton-Jacobi-Isaacs equation, whatever you want to call it, it depends on the problem you're solving, then this is zero if I have the optimal ones. But since I use approximators, so my Hamiltonian won't be zero anymore. But I want to drive it to zero, okay? So we go back to our adaptive control folks and our adaptive control books, and I see, okay, so what is the way to find a weight to take an error to zero? Okay, so is to define a new performance. Okay, a new performance is given by what you see here. Okay, so again, I want to find my WIs such that my EI is going to zero. Okay, so the first thing that can come to your mind is to use gradient descent. Okay, so we use gradient descent, we use backpropagation, we use gradient descent, and then you see also that what we did here, we normalize it with this term here, and of course we normalize that one just for to prove stability easy. Okay, so with this guy over here that you see WI dot, I learn how good my controller is. So in other words, this is the critic. Okay, so eventually, if my EI goes to zero, then I have solved my Hamilton-Jacobi-Isaacs equation. Okay, and again, this sigma I, okay, for now, we will depend on the dynamics. You will see soon that they will not depend on the dynamics. And of course, since we use ideas from adaptive control, so these things, they inherit what is called position of excitation, which in the learning is exploration versus exploitation. Okay, and then of course, how I can do that is when I have my U, my control input, when I design it, I add some probing noise. Okay, and then I excite my system so it moves around and doesn't get stuck in local memory. Okay, okay. So of course, as I said, we have theorems that we can prove that we're very close to the optimal solution. Okay, so this is for nonlinear systems, and for linear systems we're exact because we know the solution to the cutting. And then yeah, so let's see what we can do. So again, everything that we describe here doesn't require any offline training, okay? So I plug and play my mechanisms, and then these mechanisms will get data from the trajectories, and they will adapt to the optimal solution, okay? And we term that as synchronous actor-critic framework. Okay, so remember that the policy iteration that I defined before, they had different steps. Okay, so I had the policy evaluations and the policy improvement. But what we have worked on is a synchronous version of this policy iteration. So it doesn't need any iterations. It's in a way adaptive control with an optimal performance. Okay, and of course, as I told you before, in order for us to guarantee stability, so people they have worked throughout the years to with a single critic, but we found it easier, not easier in a way, easier to guarantee the best form of stability to use also an actor. So an actor will approximate the optimal controller. Somebody will say, okay, you already find the V, but the controller depends on the VDX, right? Depends on the gradient of the V. So yeah, I mean, but we want to also guarantee stability. And if you do that, then we have to do slightly more control, which we don't like because it can cause some damage to the control systems. Okay, so this can be, so this is my actor, okay? Don't worry too much about these equations here. And then if we want to guarantee stability, then we can prove actually that the actor tuning law that will guarantee stability is given by this tuning law that you see here, okay? And again, I want my sigma to be present exciting. So these are just some definitions. Okay, so this was for the zero-sum game, okay? But what happens to the non-zero-sum game? So in order for me to not to get to confuse you with many players, I will assume that I have a two-player non-zero-sum game, okay? And both of them, they're not competing, but both of them are minimizers, okay? But both of them, they have their own costs. Okay, so now we will go back to the movie stage that I told you about, which is two critics and two actors, okay? So since I have two costs, I have two critics because I want to find two costs, and then I have two actors because I have two controllers. So you can think that I have x dot equals fx plus gx ui plus kx u1 plus kx u2, okay? And u1 and u2, they're controlling the system, but each one controls from a more from a more selfish optimization. Okay. So now, again, as since I have two critics, okay, so then I will have to find two tuning laws for the critic. Again, the same structure that we had before. I can use my gradient descent, I can normalize it, blah, blah, blah. And the two actors, again, by using the same structure. Again, as you see here, I depend on the dynamics, and then you will see in a later slide that we won't depend on the dynamics, okay? And again, for everything that we provide here, we have proofs for Lyapunov stability and proofs for convergence with optimal solution. Okay, so this is actually what I just told you about, okay? And let's see how this will work for this example, which is a nonlinear system where f of x is, has all these weird terms with the cosine and sine. My gx and my gx and my kx are also nonlinear functions, okay? So what I want to do, in order for me to see if I converge to the right solution, okay, I will use some inverse optimal control method, okay? So I will already know the solution to this one, which actually was in a paper by Nevistis and Prims, and then I will compare it with my solution, okay? And yeah, and then of course, we were able to stabilize the system. Well, you see all these oscillations, they're due to the probic noise. And then we will eventually convert to the optimal solution, okay? So now, I mean, for graphical games, the equations seem more weird and longer, but it's actually not the case because here you don't have complete information about every other player, but you have a local information. And then for every player, you just plug and play these two tuning laws, and everyone will synchronize optimally to a leader, okay? Okay, so here's a structure. And in this structure, I also made it even more difficult. And then what I wanted is I wanted to have some adversarial information, okay? So let's say that I have a group of agents, and then I have my friendly neighbors, but I have also my bad neighbors. Okay, so my friendly and my bad neighbors, they're actually competing to solve the problem. Okay, and we use that for some double integrator dynamics, which are they can be in any dimensions that you want. Okay, so here these are the good players, and here are the bad players. Okay, so you can think that I have 10 agents. Okay, 10 agents, and every agent has a good player and a bad player in its own subsystem. Okay, so again, we were able to solve all these things and make we converge to that solution, the offline solution. So here's some plots. Just don't worry about this too much because it's I haven't shown the offline version. But yeah, so we converge to the offline solution. Let's see now that what you can do to solve Hamilton-Jacobi-Bellman equations, again, that they evolve in continuous time, but my controller is not updating continuously, but updates only when it's needed. So then we developed what is called event-triggered synchronous reinforcement learning that solves Hamilton-Jacobi-Bellman equations where the U updates only when it's needed, okay? And then when it's not needed, I just use zero-order Hall, okay? And of course, my Hamilton-Jacobi-Bellman equations here, they won't be zero anymore, but there will be the difference between if I had a fully time-triggered controller minus my event-triggered controller square, okay? So of course, you can see that if my time-triggered controller and my event-triggered controller has infinite updates, so then this will become zero, and then I go back to my Hamilton-Jacobi-Bellman equations or Hamilton-Jacobi-Isaacs equation I have. Okay, so this actually was the reason that we did that is we want to reduce controller updates, and of course we have to pay a price for that because we're losing some performance. Okay. That this was especially used in large-scale cyber-physical systems. Okay, so this is the sample controller that I told you about. Okay, so you see that between two time instants. Okay, so this is the classical optimal control that comes from minimizing the Hamiltonian. Okay, so xj is the state is the time that is the point in my state trajectory that I want to close the loop. Okay, and you determine the RJs based on some conditions. Okay, so these conditions they have to do on when I'm going to become unstable, on when I'm going to really get far away from my optimal performance. Okay, so we found these conditions, and we still proved that the system is stable. So you can think, I mean, now what I have done here is I substituted my U with sample components. I substituted my Hamilton-Jacobi-Bellman equation. Of course, as you can see here, this is not zero anymore, as you can imagine, okay? But this will be a residual, okay? Again, here I haven't used any approximators, okay? But this is just the offline solution here. Okay. Again, my tuning law for my gradient, for my critic, it will be the same because the cost is continuous, right? The cost will measure the state continuously, but my actor will have a zero-order hold component that you will see pretty soon. Here it is. So again, the first tuning law that you see is the zero-order hold. Okay, so I hold my previous value until I see something that will make me jump to a new value. So the first one is continuous, and the second one is a discrete component. And then we actually handle stability in this one by using the structure of impulsive systems. And then we have to prove what the stability between jumps and other jumps. Okay. Okay. And then, as I said, this will follow an impulsive closed loop system. Okay. Again, somebody might wonder. Okay, so what are the conditions that you can guarantee stability? So we found the EJ, which is the gap. So the people in event trigger control, they call of what is called the gap. Okay, so this is the state minus my sample state. Okay, so if this difference, the quadratic one, I mean, the good condition is when this is less. Okay, so if it gets violated, so then I close my loop. Okay, and then of course we also have to have conditions for how fast you tune your critic and all these things. And here we can prove that our closed loop signals are bounded. Okay, we cannot really prove that the equilibrium point is asymptotically stable, and this is because of all these approximators that we have used. Okay. Okay. So the previous one was for regulation. Of course, we have used it also for optimal tracking. Okay. Optimal tracking is a very interesting thing in controls because there are two equations that you have to solve. Okay, one that goes backwards in time, the one that goes forwards in time, and actually three equations, and the one that connects those two. Okay, so we found a way, and then we modeled the tracking as, and of course, we don't want also people they have used in the literature. They have also found the desired control, the UD, and then they plug it into the system and they check how far their U is from the U desired. But we don't want to do that. We want to do with one shot. We want to solve one Hamilton-Jacobi-Bellman equation, and this Hamilton-Jacobi-Bellman equation will guarantee optimality of the tracking controller. Okay, so one thing that we can do is we will augment my dynamics, and I will redefine my dynamics. Okay, so I will augment my system with an exosystem. Okay, and but of course, since I want to make sure that my cost is finite, I have to also use exponentially decreasing cost that you see here. Okay, and also another thing that I have to do is the Q augmented here that you see, it has to have a structure. Okay, so the structure is that I don't want to penalize my exosystem, okay? Because the exosystem comes, okay? So I want to only penalize my tracking error. So for example, in the X augmented, where my first will be my augmented error and the second one would be my exosystem, I will put 1, 0, okay? Okay, and of course, again, so now I don't have only my, I have another kind of Hamiltonians, Hamilton-Jacobi-Bellman equation, and then this has some extra terms because I have exponential decreasing noise. Okay, exponential decreasing cost. Sorry. Okay, again, we use similar techniques to find the critic, and again, we used similar techniques to find the actor, and we were able to track different cases. Okay, sinusoids, cosines, and then while we were optimal. Okay, so when you do such techniques, okay, so you also have to prove that your triggering is Zeno-free. Okay, so what that means, Zeno behavior is one, you have infinite switches in time instants. So we want to avoid that. Okay, so again, we prove that for these specific triggering conditions, we can pick our tuning parameters and all these things such that everything is good. Okay, and of course we also prove several things regarding to Z. Okay, so another interesting thing that we have developed through the years is we developed some solutions for Stackelberg games. Okay, so for those of you, I'm sure all of you are familiar with this one. So Stackelberg games are non-zero-sum games that they have hierarchical decision making. Okay, so of course, Stackelberg games they can be defined as open loop, closed loop, or feedback. Okay, and then of course it's not what in controls we call open loop or closed loop. Okay, so you will see, and then here in this presentation I will talk to you about open loop, and then you will see what this means. Okay, so I have a subset of players that they will act as leaders, and a subset of players that they will act as followers. Okay. So here I will say that let's say I have two players now. Okay. So let's say that my player one is the follower and my player two is the leader. Okay. So the leaders, they know the follower's decisions, but not vice versa. Okay. And then this is just a classical Stackelberg equilibrium definition. So suppose there exists UI star and U2 star on the reaction set of player I, then for any pair U1, U2 on the reaction set of player I, the pair U1, U2 is defined as a Stackelberg equilibrium with player 2 as the leader. Okay. So in order for me to solve such things, let's again assume a classical controls problem. Again, I will assume that U1 is the follower and U2 is the leader. Okay. And this will be a sequential optimization. Okay, so one announces the strategies and then it plays. Okay, so here we will not do it over infinite horizon, but we will assume that we have these structures for our costs. Okay, and then we will try to see what we can do to develop my Stackelberg solution. Okay. Again, so here, as you can imagine from what I have said before, I will have two costs. Okay, one cost that it will be for the leader, and one cost that will be for. Okay. Again, for me, the leader will have one more constraint. This will be how the follower reacts. Okay. Now, as I said, I have two critics and I have two actors. Okay? Now, the tricky part will be that I won't employ costs, but I will use something that seems like a potential function. Okay. So lambda 1 and lambda 2 here, they are the Lagrange multipliers that connect my two players into my performances or my Hamiltonians. Okay, again, I will assume that one, let's say since I have a linear system, one will solve one Riccati, okay, if it exists actually, and the other will solve another Riccati. But again, these two Riccatis will be connected through the reaction set of them. As I said here, the reaction set of the follower. Okay. Okay. Again, these are my controllers. Okay, for the two players. And now here's the tricky part. Okay, you remember before when I did NAS games, both of them they have similar structures. Okay, but in a Stackelberg, the Hamilton-Jacobi equations they don't have similar structures because it's a sequential optimization problem. Okay, and then here you see that, as you remember, one is the follower, other is the leader. Okay, so this term here, the one with a Y transpose, will take care of how the follower reacts. Okay, and of course I want to take both these errors to zero. Okay, and again I will use similar things. Okay, and now they will not look the same with before, but let's say they're still doable. And yeah, so and then we converge to some scenario, and then we compare it with some work by Tamer Basar from Illinois. And then we eventually solved online. Again, these are plug and play techniques. And then we converged online, which is offline solution. Okay, and then we provide proofs for asymptotic stability of the equilibrium point given certain conditions on the weighting matrices. Okay, now, up to now, I told you, and before I end my talk, I told you about all these techniques, but all these techniques, they require knowledge of all the system dynamics, f of x, gx, kx, blah, blah, blah. So we developed, with Frank Lewis, we developed something that we termed as integral reinforcement learning. So instead of defining the Hamiltonian, and then find the stationarity condition based on the Hamiltonian, we use an integral form of the Hamiltonian. Okay? And then this actually will make us model free with respect to the drift dynamics. And so you also prove that this integral Bellman equation that you see over here, it's actually the Hamiltonian that you saw before. And of course, we have conditions for a small enough t. Okay? And of course, if you take this to 0, then you will eventually converge to your Hamilton. Okay, so again, we use the same techniques here. Okay, so your V will be approximated, okay, by a critic. Your U will be approximated by an actor, and then you will eventually want to make this EI to 0. Okay, so you can assume that I take everything on the left-hand side, and then this will be equal to 0. And then, but if I have approximators, this won't be 0, and then I will take it to 0 by using adaptive control because I did before. Okay, and again, we will eventually then solve this problems that you saw before by doing this modification here and by doing this modification in my critic, okay? And then I will convert to the same exact solution. Okay? So now my critic, as you see here, and remember, delta phi's are just differences on your bases, okay? So now your WC doesn't depend on f of x, okay? Neither gx. But of course, my controllers, they depend on g. So the only available information now, I will say, is my g, okay? My g and my k. But I don't know my drift dynamics, and I can still convert to the same solution as if I knew the system. Okay, and then we have done it for different kinds of games, and we have exactly the same solution, and we proved that the two things that we described before, they're the same. Okay. Of course, we can go back and do everything model-free, and then we can use Q-learning mechanisms, okay? And again, the idea is the same, but we have to redefine what is called an advantage function. An advantage function for this scenario will be, what if I knew the optimal cost that you see VI star plus the Hamiltonian of the system given VI star, which only for the Lagrangian? Okay, remember, if I take if I plug in all my U's and my V's, you can think that this is the scenario that I had a graphical game where I have different U's and different V's. So V's are the bad players, U's are the good players of the system. So then this becomes 0, and hence my QI star and my VI star, they have the same cost. So then my problem didn't change, okay? And then we can do that in a similar framework, and then we can have finally model-free versions of everything that I have decided. And again, this actually relaxes to the integral form of the Bellman equation, okay? Again, there is no offline computations. I plug and play these three things in every agent, and then it will converge to the optimal solution. Guaranteed stability and convergence. Okay, and then these are some theorems, but I don't want to bore you with this one. So I want to show you some interesting simulation results for now. So let's say I have a graph of 10 agents, okay? And the leader is only pinned to agent number 6. Okay, and you can think that this is a human leader. Okay, and then everything else is heterogeneous systems, which can be flying systems, ground systems, blah, blah, blah. Again, I have a good player and I have a bad player. Okay, the bad player will change my actuator data. Okay, so let's say I run it without any framework, even offline. So then you see what happens, right? So my states will never synchronize and will explode. Okay? But what happens when we use our own learning framework? Okay, so here in this graph here, you see the leader agent is the green one, and then everything else, the circles, are the agents that start from different random initial conditions, and all of them synchronize to the leader without even communicating with him. If you see here, only number 6 communicates. And not only synchronizing, but they're also converging to the optimal solution of the problem. So, yeah, and then to conclude, I think right on time, okay. So this is some part of our research that we work on how do groups of agents learn about the environment and then act to achieve robust, secure, stable, optimal, and effective coordinated behaviors. We provide these mechanisms for online learning of large-scale games. We prove that everything converges and everything is stable. Of course, there are many things that we have to do, okay? Especially in this forum that there are many people that they work on different things on Hamilton-Jacobi equations. I will be happy to talk about how to incorporate learning into viscosity solutions of Hamilton-Jacobi equations. Okay, how to, when you try to find these Hamilton-Jacobi solutions, how do you actually share private and public information? And also about adversarial learning. Yeah, and then many other things, but I think we're running out of time. And with that, I would like to thank my several collaborators through the years, my funding agencies, and then thank you for paying attention to my talk. And I will be happy to answer any questions.